The Bureau of Land Management Satellite Network presents live from the BLM National Training Center in Phoenix, Arizona, Acid Rock Drainage, Prediction and Treatment, Course 3000-47. And now, the host of your program, Dave Williams.
Well, good morning. Welcome to the National Training Center for our course on acid rock drainage. Due to the web confusion, you may have downloaded some information either from the ADTI website or the BLM's intranet website. This material contains information and illustrations that you may find useful for taking notes. We may refer you to the page in the notebook, but if we don't cover something and you have a question, please feel free to email or call us. Our objective today is to provide you with a good technical foundation of acid rock drainage as it relates to permitting new mines, oversight of operating mines, and remediation of abandoned mine lands, or AML. Here's a quick overview of what we'll be covering today. We're going to look at geology and the natural environment, the geochemistry of mine waste dissolution, sampling and monitoring, characterization, drainage quality prediction, mitigation and cleanup, bonding, and mine closure. And let's also talk about what we're not going to cover. We're not going to talk about acid rock drainage from coal mines. While the basic process is the same, there are some very important differences between coal and metal mining, and we're going to be dealing specifically with ARD related to metal mines. We're also not going to cover the biological impacts of acid rock drainage. Acid rock drainage can have a large range of biological impacts, but they're well beyond the scope of what we're going to cover in this session. Although we will talk about some biology related to acid rock drainage, such as the role bacteria can play in the development of acid rock drainage. I'd also like to mention the Acid Drainage Technology Initiative of the Metal Mining Sector, or ADTI-MMS. This group is a consortium of government, industry, academia, and consultant companies working to develop scientifically based solutions to acid drainage problems for the mining industry. If you're interested in additional information on ADTI-MMS, again, please check the website at www.mackey.unr.edu/ADTI. Well, before we really get started in the program, here's a few housekeeping details. As you can see in your course workbook or the satellite information, this is an all-day training session. We'll take an off-air break at midway point to give everyone a chance to grab some lunch, and there'll be some short breaks throughout the day. Throughout this program, we do want to hear from you. If you have questions or comments, you can call us toll-free at 1-877-709-5340. Sites in the greater Phoenix area should call 602-943-2279. We have several question and answer segments planned during this training. In addition, if you have a question for us, go ahead and give us a call at any time, and we'll get to your questions as soon as time permits. You can also send us a fax at any time. The fax number is 602-906-5701, and we'll get to your questions during a break or whenever we can. So now that the logistics are out of the way, just what is acid rock drainage? I'm going to give you only really the basics on acid rock drainage, Chemistry 101 or lower, and the rest of the presenters are going to carry on from there. And the basics are, you take sulfides, you add water and air, and the reaction goes to metals in solution, sulfate in solution, and hydrogen ions, which of course are part of the acid, part of the equation. So let's look at the what we call the ARD tetrahedron. And this is a concept we'll carry through the presentation, and it looks like a tetrahedron. The corners of the tetrahedron are water, oxygen, sulfide minerals, and generally these are iron sulfide minerals, and bacteria. During the course of the presentation, you'll become familiar with the ARD tetrahedron and the role each of the corners can play in limiting the ARD reaction, and also in limiting the transport of produced byproducts, usually acid and metals, as well as the potential ideas for remediation that come from the ARD tetrahedron. Now, to set the stage for our training, let's look at an operating mine in Montana, which is taking some measures to mitigate potential acid drainage. We're here at the Golden Sunlight Mine. We're about 30 miles east of Butte on what is a cool and blustery July 31st, as you can probably tell. Golden Sunlight Mine was permitted in 1981. Construction began in 1982. They poured their first gold in 1983. It's a gold mine. They mine gold from a pyrite-rich brecciapite in the mine. We'll be looking at the mine in kind of a general overview, and then we'll also look at some of the things the mine has done in response to the potential for acid rock drainage and in response to the agencies that permitted it, which was the Montana Department of Environmental Quality and BLM. We'll look at some of the waste dumps. We'll look at some of the work the mine has done in terms of monitoring and also waste dump construction. And hopefully as we go around the corner, the wind will let up a little bit. We're on the west side of the Golden Sunlight Mine. This is the west waste rock dump complex. One of the major issues in the permitting of the mine over the course of several years was the successive reclamation of the highly acidic waste rock. The agencies would have preferred that the slopes be reduced to 3-to-1, but the mine wanted 2-to-1 slopes for economic reasons and also in terms of slope disturbance. You would disturb less native ground of the 2-to-1 slope than a 3-to-1 slope. So these were originally permitted as test reclamation plots, and this behind me is a 2-to-1 slope. It has about 10 years growth on it. It was seeded in 1992, and as you can see, it's a fairly steep slope. The reclamation called for 24 inches of oxide rock and 19 inches of cover soil, and you can see the cover soil is quite coarse. And behind me is a data logger, a solar-powered data logger, which accumulates data from these access ports. These tubes provide access for some of the monitoring that was done of the waste rock dumps. And there are several sites like this at the mine. This is just one of several. These access ports provide access for measuring water that's going into the dump, measuring temperatures in the dump, measuring gas composition in the dump, which gives us a pretty complete readout on the oxidation of the waste rock in the dump. We have several years data accumulated from this, and it supports the idea that the cover system that we've put on here and the mine has put on here is effective in reducing infiltration into the dump, which of course ultimately limits anything that comes out of the dump in terms of acid rock drainage. So that's some of the things the mine has done and the agencies have reviewed in terms of dump cover performance. So, as you've just seen at the Golden Sunlight Mine, some of the measures used went beyond what's normally recommended as standard reclamation practice, as well as the extensive monitoring that was included as part of the mine permit. Well, at this time, I'd like to introduce the instructors who will be getting us started on the serious stuff. Joining us this morning is Virginia McLemore, an economic geologist with the New Mexico Bureau of Geology and Mineral Resources, which is a division of the New Mexico Institute of Mining and Technology. Virginia has studied the geologic setting of mineral deposits in New Mexico, including environmental impacts, for 21 years. Good morning, Virginia.
Morning, Dave. I look forward to the opportunity to present some of my experiences in New Mexico on sampling, monitoring, and geology.
Great. It's good to have you. Also with us this morning is Harry Posey. Harry is an economic geologist and isotope geochemist with the Colorado Division of Minerals and Geology, and though he will deny it, Harry has been involved with the Summitville cleanup in addition to his other responsibilities. Good morning, Harry.
Good morning, Dave, and I promise that's the last mention we'll have of that particular mine.
Okay, I'll make sure it is.
Great.
Virginia and Harry will be giving us an overview on geology and the natural environment. And at this point, you can begin following along in your workbook on page 5. Virginia, I believe we'll start with you.
Thanks, Dave. The object of this section is to show how geology and physical and climatic conditions affect the formation and migration of acid drainage. If you turn to your geology section in your workbook, which begins on page 5, you will find some of the slides have blanks. As I go through this section, follow carefully so that you can fill in the blanks with the correct answers. The most important step in evaluating a site for acid drainage is to characterize and understand the geology and the natural environment. This would include the physical and climatic conditions, and this is for 3 major reasons. First, the entire ecosystem being remediated must be understood in order to have successful remediation and control of acid drainage. Second, the extent, sources, and effects of potential contamination must be characterized and prioritized. And third, the pre-mining conditions must be estimated in order to establish realistic and affordable remediation goals. It is important to remember that regulatory and scientific objectives should be based upon the natural conditions at the site. Some of the components of characterizing the geology and natural environment include, and this is just a laundry list, knowledge of the regional geology. This would require geologic maps and cross-sections. Establish the background and existing conditions. Characterize the baseline conditions. Identify and quantify existing and potential sources, geological, the transport or migration paths, hydrologic and geologic, and the effects of potential contamination. And this is where we're looking at biological, which are really the key issues. Additional components of characterizing the geology and natural environment include characterization of target sites and processes affecting the contaminant dispersal. You must characterize the geology and natural environment in order to develop remediation goals and monitoring studies. And finally, I can't emphasize this enough, document the lessons learned for future applications, even if they are rare failures. Let's learn from our mistakes. Some questions to ask during a regional and/or site characterization include, and I'm just going to give you a laundry list. What is the purpose or objective of your project? What are you going to look for on a site in order to develop successful remediation plans? How do you develop a site characterization plan? How do you identify impacted mine, human, agriculture, other areas versus pristine areas? How do you interpret subsurface and geologic and hydrologic data? What types of monitoring may be required? Can you think of any other questions that you would ask? Take a second now and write them in your book, and you can share them later on with us. To answer these questions, a variety of data for characterizing the geology and natural environment must be collected and should include the following. Knowledge of the climatic conditions at the mine site is crucial in understanding the formation, migration, and control of acid drainage. One of the very first things a company should do is to establish a weather station at the mine site, even during the exploration stage. The earliest data can be collected, the better. Precipitation at the specific site is needed, which is also critical in groundwater models and modeling of acid drainage. Too many times precipitation and flood potential data from tens or even hundreds of miles away are used and can result in erroneous predictions and modeling of acid drainage. The type of climate, arid, humid, mountains, and so forth, controls the amount of water available to generate acid drainage. It also is important to understand that microclimates are common at many mine sites. It is important to remember that the environmental impacts may be delayed in semi-arid and arid environments, especially at high elevations. Some specific climatic data required, and I'm going to just give you a list. Temperature, evapotranspiration, rainfall, snowfall, river flow, floods, 10-year, 100-year, freeze-thaw actions, growing season, days of sunlight. Many of these data are required for the environmental plans, the mine plans, metallurgical processing, as well as specifically to understand the formation, migration, and control of acid drainage. Some of the physical data and characteristics required for a regional characterization include topography and altitude. The topography plays important roles in the type of mining method required, as well as the extent of the disruption and disturbance of the land surface and the impact on water and drainage quality. Detailed topographic maps are essential in identifying potential pathways of acid drainage. Are the drainage systems natural or are they man-made? What is the predominant wind speed and the wind direction? What are the characteristics of storm events and what types of storms occur? What are the stream flow measurements? Well, we have summarized some of the climatic and physical data we need for a regional or site characterization. Now let's talk about my favorite subject, geology. Generally, metal mining is more diverse and more complex and can have more environmental effects than most coal and industrial minerals mining. Primarily, this is a result of the different types of metal deposits and their unique occurrence in the Earth's crust. Because metal deposits have such complex geology, mapping of the structure, including location and character of faults, joints, fractures, and extent of the deposit, are needed. Some of the lithologic and stratigraphic factors that affect mine drainage quality, which should be mapped, include the presence of limestone, other carbonate rocks, andesite, or other rocks that could neutralize acid drainage. Here is a sample of limestone. It has a brachiopod in it, and we can take acid and do the fizz test, and you see the nice bubbles. Here's another sample of limestone that we actually see some crinoids. And these are common. Some limestones will be fossiliferous and some will not. We also see the presence of altered rocks around these deposits. And here's some mafic rock, a nice volcanic rock, pluton that now is altered by pyrite, which you really can't see at this scale. And then the white in here is quartz veins. The type of mineral deposit dramatically affects the potential impact on drainage quality. Different deposit types contain different suites of minerals and characteristic geochemical signatures that may impact soil, sediments, and drainage quality around mine sites. There are many reports that describe the different types of mineral deposits. These references are included in the student workbook and on the website. Mineralogy is a major factor in controlling acid drainage. Although pyrite is the predominant mineral that produces acid drainage in metal mines, other sulfide minerals as well as other minerals may play important roles in affecting the drainage quality in and near the mine sites. I'm going to show you some pyrite cubes. You may not actually see this caliber of pyrite in the field, but it does give you an idea of what pyrite looks like. Note the brassy color and the metallic luster. Pyrite also is a relatively hard, and a knife blade will not scratch it. Dave, back to you.
Thanks, Virginia. Before we go on, I may have given you some bogus information on the phone number for people in the Phoenix area. If we could go to still store 9257, we'll try and get that right number out for the Phoenix area callers. We'll get it to them as soon as you can. But the number, in the event we can't get it up right now, is 602-943-2279. So with that, we do now have a short video on geoenvironmental models prepared by Jeff Plumley, who's an environmental geochemist with the Geological Survey in Denver. The objective for the material that Jeff's going to present in this tape is for you to understand what a geoenvironmental model is and how it can be useful in evaluating acid rock drainage potential. So without further ado, here's Jeff.
There are a wide variety of considerations that must be taken into account when trying to understand and address potential environmental impacts of proposed, active, or abandoned mining operations on federal lands. Examples shown on this first slide include potential mining and processing related issues, such as mine dewatering, generation of acidic and/or metal-rich mine drainage, disposal of potentially large volumes of mine wastes or mill tailings, potential accidental release of mineral processing reagents, dust control, and smelter emissions or disposal of smelter wastes. Being able to assess or infer pre-mining baseline conditions is also absolutely essential to developing appropriate and effective environmental remediation standards for proposed mines, mines in closure, and abandoned mines and processing sites. The bottom line is that the geologic characteristics of mineral deposits, as well as geochemical and biogeochemical processes, play fundamental roles in every one of the environmental considerations that may arise from mining and mineral processing. There are other controls, of course, such as climate, the types of mineral processing or mining methods used, which are also controlled by deposit geology, and the effectiveness of any environmental prediction, prevention, and mitigation measures that are used. However, these other controls are all ultimately influenced in some way or the other by geologic and geochemical processes. Economic geologists have long recognized that mineral deposits can be classified or grouped according to similarities in how they form and similarities in their overall geologic characteristics. As a result, mineral deposit models have been developed that describe or summarize all of the important geologic characteristics of a number of different deposit types. Because these same geologic characteristics control geoenvironmental signatures, such as mine drainage compositions or smelter compositions, it's also appropriate to develop geoenvironmental models of mineral deposit types. Geoenvironmental models describe pertinent earth science and engineering information about the environmental characteristics of geologically similar mineral deposits. For example, for deposits of a given type, the geoenvironmental model summarizes available empirical data on the compositions of mine waters, mineral processing solutions, and natural waters draining mineral deposits prior to mining. Other empirical data sets include pre- and post-mining data on the compositions of soils and stream sediments in mining areas, and on the compositions of other environmental signatures such as smelter emissions. The models also summarize, for example, typical historic and modern mining and processing methods that were used, which can vary considerably depending on the geologic characteristics of the particular deposit type. In the next few slides, I'll pull together the environmental geology principles that I've just discussed and show how geoenvironmental mine drainage models can be developed for two geologically different deposit types. Summitville is a gold deposit that's located in the San Juan Mountains of Colorado, and it's a type of deposit known to economic geologists as an acid sulfate epithermal deposit. These deposits are commonly hosted by volcanic domes and formed as a result of volcanic and hydrothermal processes accompanying dome formation. The key aspect of these deposits is that volcanic gases are released from crystallizing magmas at depth, rise along fractures to shallow levels in the dome, and condense. This creates highly acidic fluids that leach their way outward from fractures into the surrounding dome volcanic rocks. Especially in the main ore zones of the deposit, the dome host rocks are extensively leached by these acidic gas condensates, creating acid sulfate altered rocks with little else than silica and acid stable sulfate minerals such as alunite and jarosite. Hydrothermal fluids then use the same fracture system to deposit pyrite, an iron sulfide, enargite, a copper arsenic sulfide, and other copper sulfides. The end result is that the main ore zones of this deposit type have high acid generating capacity but very little acid neutralizing capacity. This slide is a plot of the pH and base metal content of mine waters and natural waters draining a variety of acid sulfate epithermal deposits. The waters draining the main ore zones are, as would be expected based on the geologic characteristics I summarized previously, highly acidic with elevated levels of iron, aluminum, copper, and arsenic. In the distal alteration zones of these deposits, where carbonate minerals were actually added to the rock by alteration processes, the drainage waters have much higher pH values and much lower metal contents. Note that the natural waters draining unmined mineral deposits of this type can be quite acidic, but they tend to have lower concentrations of copper, zinc, and other heavy metals than mine drainage waters. Such data can be used to infer likely pre-mining drainage signatures in a mined area. This next slide is a photo of a sediment-hosted gold deposit as seen in an underground mine working. Deposits of this type, which form the majority of currently working gold deposits in Nevada, are characterized by the common occurrence in carbonate sedimentary rocks. The deposits form by the reactions of acidic and arsenic-rich hydrothermal fluids with the carbonate wall rocks. Decarbonatization, or removal of carbonate from the host rocks, results in the dissolution of calcite from the host rocks and the deposition of a silica-rich jasperoid with very little acid neutralizing capacity. At the same time, the hydrothermal fluids deposit abundant arsenic sulfides, pyrite, and microscopic gold in the decarbonatized rocks. In this slide, you can see the abrupt boundary between decarbonatized rocks with abundant yellow-orange arsenic sulfide minerals and the unaltered carbonate host rock with abundant white carbonate veins. I hope that I've given you a fair amount of information that shows how we can develop mineral deposit models and also how we can apply this information to develop geoenvironmental mineral deposit models and how these can be used by land managers such as yourselves to better understand and address mining-related environmental issues on federal lands. Thanks very much.
Well, as Jeff has demonstrated, similar mineral deposit types can be expected to produce similar environmental signatures, and we'll talk a little bit more about that. It's important to note that while geoenvironmental models can give you a good idea of acid drainage potential, it's still important to know the specifics for each deposit. This is just one of the tools in your toolbox. Virginia and the rest of the presenters will be talking about some of the others, and with that, Virginia, back to you.
Thank you, Dave. In the 1990s, as you just saw, the USGS redefined their classification of mineral deposits in terms of environmental geochemical classification. This is by Dubray, 1995, and Plumley, who you just heard on the tape, in 1999. Please see the website for the specific citations. Why are geoenvironmental models important? Well, for at least 6 reasons. The geoenvironmental models describe the geology and mineralogy of the deposit type. They describe the typical mining and milling methods that you will encounter. They provide data on the trace element geochemistry of the deposit type and what elements may actually end up in your water. They provide data on the metal mobility from the solid waste. They summarize drainage signatures. They provide guidelines for potential migration and remediation for some deposits. On the web page, I've included a section from the USGS report on geoenvironmental models. This is the first page from the section on porphyry copper deposits. I don't expect you to see it on this slide, but this will give you an idea of what it looks like. Now let's take a look at a table that includes geochemical data that you can compare from the data obtained from your project. This is also on that section and in these models. You can use these data to estimate the geochemistry of your project, provided yours is the same type of ore deposit. In the case of a porphyry copper deposit, let's say you want to know what trace elements are likely to be found in the outer halo of the chalcopyrite zone. From the table, you would find that the following elements are listed: silver, arsenic, gold, boron, copper, lead, iron, molybdenum, selenium, tellurium, thallium, zinc, among others. Now, do you think sampling and monitoring and reclamation plans should at least be looking at the distribution of these elements at your site? The USGS report will assist you in recognizing different deposit types and their general effect on the environment. This is only a general guide. Site-specific conditions will and do vary from the models. Let's discuss alteration. Alteration halos are common surrounding many metal deposits. Country rocks surrounding most metal and some industrial minerals deposits exhibit reaction effects from circulating waters that can change the mineralogical composition by physical and/or chemical means. During formation of the mineral deposits, some elements may move from the host rock into the fluid, while other elements move from the fluid into the host rock. The altered country rocks vary in extent from a few millimeters to many kilometers from the vein or mineral deposit and form alteration zones, halos, envelopes, or selvages. The extremely altered rock may be acid generating, whereas the less altered rock may be acid neutralizing. Here are some samples of some of the grungy, altered rocks that you may actually see around mine sites. They're often brown in color. They will sparkle because of the pyrite, and they will often have quartz. It is important to realize where you are in the alteration sequence in order to have successful remediation and control of acid drainage. The alteration zones or halos are typically more widespread than the actual mineral deposit and can aid exploration geologists in locating the mineral deposits. Clay alteration also is common in many mineralized areas and may actually neutralize acidic drainage, although it may take a long time. Alteration zoning further complicates drainage quality in many mineralized areas because of the presence of pyrite. How do you recognize alteration halos that might cause acid drainage? Look for bleaching of the rock, the presence of pyrite. The predominant colors of the altered rock are shades of red, orange, brown, and white. You may even notice a smell of sulfur when you break open some of the rock. This is due to the pyrite and sulfate minerals. Here is a view from the air looking east at the natural alteration scars associated with Molycorp's Cuesta mine near Red River. The Goat Hill Gulch scar is in the foreground below the mine dumps. Here are the mine dumps. And Red River is over here in the valley, and you can see these alteration scars. These are natural scars, and Red River's in New Mexico. These alteration scars are related to the mineral deposits. Molybdenum in the case of the Red River deposit, the molybdenum Cuesta deposit, and gold and silver at Red River. And they are acid generating. Note the bright red-orange colors. Now, how do you distinguish between natural scars and man-made cuts? Well, you have to know the geology and the mining history. Visual examination may be deceiving. Zoning, including the chemistry of the site, must be understood. And it is very important to know what elements are in the deposit as well as adjacent to the deposit that could result in metals being mobilized by acid drainage. For example, here is a geologic map of the Carlisle mine area in the Steeple Rock District in southern New Mexico, near the border with Arizona. Epithermal gold, silver, copper, lead, zinc veins are found along these faults, shown here in solid black lines right there. Drainage from the mine, a pit which fills with water periodically after storms, shown here in blue, is found at the mine site. Drainage from this mine area is to the south and is sometimes acidic and eventually drains into the Gila River in Arizona. Alteration zones are shown in color. Red is the massive silica chert zone that is characterized by quartz, illite, and pyrite. Orange is the silicified zone characterized by minor pyrite, quartz, and clay minerals. And yellow is the clay zone characterized by clay minerals. The red zone, the massive silica chert zone, typically contains elevated levels of arsenic. From the distribution of these alteration zones, you can infer the distribution of the potential acid-generating rock, the massive silica chert and silicified zones, in relation to the pit and the mineralized faults. These are the red and orange zones. These are the potential problem zones. Any remediation of this particular mine would have to consider drainage from these two zones in order to reduce or eliminate acid drainage, because these zones also may contribute to the overall acid drainage from the mine site. Knowledge of the geochemistry of these zones is crucial to know what metals may be mobilized. Other geologic factors that should be examined include, and I'm just going to give you a quick list, ore body properties, subsurface geology, particle size analysis, which affects surface and groundwater flow, geomorphology, seismic data, including earthquakes. Well, now let's talk about hydrogeology. Hydrogeology includes both the surface and groundwater factors affecting mine drainage quality. The environmental impact on water and drainage quality is typically related to a specific type of metal deposit. In particular, deposits containing high concentrations of pyrite and other sulfide minerals are specifically susceptible to acid mine drainage. Some of the hydrogeologic components to keep in mind include surface and groundwater interactions, surface water, which typically originates from meteoric water, precipitation. The chemistry, both dissolved and particulate, of the water is dependent upon the chemistry of the air, geology, biology, through or over which it flows. One way of looking at the relationship of water to the types of mineral deposits is by the use of the Ficklin plot. This is another USGS tool in your toolbox. The Ficklin plot shown here is a plot of pH versus total metal content, the sum of dissolved zinc, copper, cadmium, cobalt, nickel, and lead concentrations of mine waters draining from diverse mineral deposits. The purpose of this plot is to predict the metal content of waters derived from specific types of mineral deposits. For example, if the mineral deposit is a pyrite-rich, massive sulfide ore, the field A shown in green, then the waters derived from that deposit are likely to have a low pH with a high total metal content. On the other hand, if the mineral deposit is a pyrite-poor gold tellurium vein and breccia deposit with carbonate gangue, the field K shown in yellow, then the waters derived from the deposit are likely to have a higher pH with a low metal content. Also, if you know the water chemistry, you can use this plot to predict what mineral deposits might be in your area, but I suggest you map them and visit them yourselves. It must be emphasized that this should be used as a predictive tool and is not absolute. Some waters from specific mineral deposit types may plot outside of the indicated fields. Well, let's continue on and let's talk about some of the surface and groundwater factors affecting mine drainage quality. Porosity, permeability, and grain size of the host rocks control groundwater flow and saturated versus unsaturated zones. The pH, heavy metal concentrations, and concentrations of other elements, in particular aluminum, iron, and sulfate, are very important. Total suspended matter and resultant turbidity is important. Here is an example of a cross-sectional view of the subsurface geology at a sandstone copper deposit in Poland and the variation in groundwater flow in the different layers of rock. Note that the water flows vertically as well as horizontally. The direction of groundwater flow changes as a result of geologic conditions of the aquifers. Any remediation of this site would have to consider these variations. Well, let's talk about mining history and the effects of mine workings on drainage quality. For instance, was there pumping or dewatering? Were there open pits for water to collect in? What types of mining methods were employed? This here is the Argo Tunnel at Leadville, Colorado. The type of processing techniques used must be identified because they dramatically affect the potential impact on drainage quality. This is an acid, the SXEW plant at Tyrone. For example, you will see different types of mining methods. What mining methods were employed at the site, and they may vary with time. Here is an open pit operation. Here is some of the pipes on a heap leach. You can see the dripping water. Here is the top of that heap leach pad, and this is probably a site in Nevada. Here is some of the dumping and the conveyor belts and the moving of rocks, an underground operation with the load haul dumping, and then some of the blasting. This is some of the blasting and some of the open pits, and they are this unique in actual use. What mining methods were employed at the site? Where are the existing openings? Are they covered by brush? What processing techniques were used? What were the operational units? What other infrastructural and cultural features existed? This would include roads, water intakes, sewage, landfills, so on. Was blasting used? What type of blasting? All of these factors must be identified during the regional and/or site characterization in order to have a successful remediation and control of acid drainage. It also is important to mention the operating philosophy of the original miners in dealing with the abandoned mine sites, AMLs. Historical miners had a different operational philosophy than miners of today. These miners had to make a profit quickly. Often they would high grade the deposit or just mine the high grade without taking the lower grade material, resulting in very unstable ground in some areas. Historic exploration methods commonly involve the construction of pits, shafts, and/or adits that may not have been utilized in production of any ore. These sites may contribute to acid drainage. Historical miners typically located ore processing facilities, your mills, your tailings, your stockpiles, near the production or haul shaft. The processing spoils were very often dumped near the processing unit, in many places into the existing arroyos, streams, rivers, lakes, or other drainages. There were no laws or other guidelines available to prevent contamination of nearby drainages. Metal mines were developed by underground and surface mining methods that were as inexpensive as possible. Safety and stability were not top priorities. Historical mines had as few ventilation shafts as possible in order to save money, resulting in very poor air circulation. Mine surveying and mapping was minimal to non-existent, and many of those maps have deteriorated with time. Upon depletion of the ore, many mines were abandoned. Mine waste piles and tailing piles were left as they were created without caps or vegetative cover. Surface and excess equipment was typically sold off for scrap. Well, in summary, it is important to understand the exploration, development, and production history of any mine site before attempting to reclaim the site. In the regional and characterization site study, we should take note of biological conditions at the site, including the types and locations of plants, animals, microorganisms, humans, and habitats. If you think your project might affect plants, animals, or habitats, then you want baseline data to document initial conditions. Or, in other words, if you're having a problem, then measure that biological entity, or if you foresee a problem. For example, if you are worried that fish might die because of acid drainage, then gather baseline data on the fish population. Here is a plot from the USGS showing the effect of acidity on selected aquatic species. As acidity increases, or pH, from left to right, some species are lost. Those are the ones shown in gray. Now, we haven't gotten to this yet, but remember, acidity and pH are not the same. But in this figure, the effect is the same. We will define these terms better later on. Finally, I want to briefly mention the effect of weathering on mine drainage quality. Oxidation of pyrite and other sulfide minerals may produce acid drainage. The dissolution of soluble sulfate, hydroxide, and other secondary minerals containing heavy metals may also produce acid drainage. The erosion and sedimentation will affect drainage quality in many cases. Mine stability, subsidence, may also affect drainage quality. Here is a view of a wall along the pit at the Copper Flat Mine, Hillsboro District in south central New Mexico, where weathering over the last 15 years or so has deposited copper and iron sulfates and hydroxides along the surface. After a rain, these salts dissolve and move along the bench. Close-up of the copper and iron sulfates and hydroxides along the surface, you see this view from outer space at the Copper Flat Mine. And these salts will dissolve and they continue moving downstream and then precipitate out again in this fashion. These erosional features may take years before any impact is realized. I would like to leave you with a list of sources of geologic, geochemical, and hydrologic data. More details are on the website. But there are government agencies and universities that produce theses, dissertations, and other academic type research that will be very useful. Scientific journals, and use GeoRef and other search mechanisms to find specific topics of interest. The company reports, many of the states' geological surveys have archives of such data on historic mines. The Anaconda Geologic Document Collection at the American Heritage Center at the University of Wyoming is another excellent source of information on these mines. There are a number of databases available that can be utilized, NURI, STORAT, and so on. A more complete list of these references is on the website. Well, what have we learned today? We've learned how geology and physical and climatic conditions affect the formation and migration of acid drainage. In particular, please remember that you should have geologic maps and cross-sections of the area. Climatic data, especially weather statistics, of the immediate site is essential to any study. Detailed site-specific topography is needed, especially in locating the drainage paths. We have talked about how to identify alteration that might cause acid drainage. Once you can recognize pyrite, you are able to begin to recognize rocks that might cause acid drainage. The Ficklin plot can be used to predict water quality derived from specific types of mineral deposits. Once you know what kind of deposits you have, you can use this plot to predict if the waters are likely to be acidic and contain high concentrations of metals. And finally, a complete history of the mining and processing techniques are needed. Back to you, Dave.
Thanks, Virginia. That was great. Well, now let's go to Harry.
All right, great, Dave. I like that blasting shot, all those rounds popping off coming toward you. I think I'd have been heading for the hill. So.
You should hear the music that goes with it.
Ooh,
It's even better.
All right. Well, you know, I'm going to talk about natural acid drainage. This natural acid drainage can have a lot of really interesting, physically interesting, colorful features to it. Some of these are really quite striking when you look at them. Sometimes when natural acid rock drainage source rocks are exposed at the surface, people mistake the outcrops for open pit mines because the colors and the weathering characteristics, they really look quite similar. What I hope you'll remember from this segment is that the weathering features of rocks that produce natural acid drainage tend to mimic the weathering of some mine waste rock. Not all waste rock, not all mine waste, but some. And I think you'll find this useful as you evaluate permit submittals or as you plan your own mine cleanups. Our objective in this segment is to show how natural acid rock drainage processes can be used to infer the behavior of pyritic mine waste when the waste is exposed to air and water. With a few photos, I'll show you some of the products of natural acid drainage as they appear in the field, and I'll also describe some of the chemistry behind these outcrops. I'll try to emphasize some of the practical aspects of the study of natural acid drainage and how it can be applied to mining. In this first shot, this is an area that's been subjected to intense hydrothermal alteration. That's alteration by hot ore fluids. This rock contains several percent pyrite and it produces natural acid drainage. This is Alum Creek in the San Juan Mountains of Colorado, and most of my shots will be from this area. The stream that drains through this area has an average pH of 2.8. That's from about 100 analyses or so, and it has a high pH in those analyses of about 3.4. The area is generally void of soil and vegetation, and it erodes at an extremely high rate relative to the adjacent streams. The production of natural acid drainage involves physical and chemical processes. As you might remember from your introductory geology, physical weathering includes those things like cracking, freezing and thawing, erosion, things that break apart the rock physically. As the rocks break apart, this generates a higher surface area, and minerals on the exposed surfaces can then break down chemically. Now, chemical breakdown includes the breakdown by organic acids or atmospheric acids like carbonic acid, for instance. The more surface area, the more rapid is the rate of weathering. Now, mining tends to break up the rocks mechanically through blasting and through crushing. This generates a larger surface area, and that also increases the rate of weathering. On the other hand, chemical weathering occurs as natural solutions decompose the minerals within a rock. For instance, when rocks are attacked by acids from the atmosphere or from acids in the soils or groundwater, then the minerals can dissolve. All rocks break down to some extent by physical and chemical weathering. But in rocks that produce acid drainage, those rates are considerably higher. In this next slide, this is also from Alum Creek in the Alamosa River in Colorado. You can see the very steep slopes and the characteristic V-shaped cross-section in the stream. These steep slopes and the V-shaped contour occur because the stream is undergoing a high rate of downcutting. The stream has a high gradient, there are no meanders in the stream, and there's absolutely no aggradation of stream sediments. Everything that falls into this stream bed gets washed downstream. Likewise, the rates of physical and chemical weathering are higher in mined rock. They also can erode at high rates unless they're stable. In this next picture, you can see there's almost no vegetation. That's because there's no soil. Both the low pH and the high rate of erosion preclude the formation of a significant soil horizon. And the lack of soil and vegetation allow for higher erosion rates. It's really a vicious cycle. The acid kills the plants, the lack of plants promotes erosion, erosion strips away the soils, and without soils there can't be any plants, and so on. It just goes round and round. In this next picture, you can see that the stream bank is composed entirely of rubble. This rubble slope is stacked there at an angle that really seems to exceed the angle of repose. These unstable rubble banks occur because the parent rock is, in this case, is made up almost entirely of clay and silica and pyrite, which I'll talk about the pyrite here in a minute. The clay rock has no physical strength, or very little physical strength, so it tends to disaggregate quickly and erode away quickly. As you can see in this next still, what looks like solid rock under my knife blade is really clay. My knife blade just went into this rock without any effort. The clay which forms during the mineralization and hydrothermal alteration. It just can't stand up to physical erosion, especially with all that pyrite around. Because the rocks break down so fast and wash downstream, the banks don't get a chance to collect vegetation, so they remain unstable. They erode constantly, the soil washes away. That was a look at some physical weathering characteristics. Now let's go to chemical weathering. In this slide, all the little thin black lines are veinlets that are filled with pyrite. These pyrite veinlets are a stockwork within this rock. The pyrite here generates acid almost constantly if it's exposed to air and water. As you know, pyrite mineralization like this, is a common feature around rocks that appear around ore mineralization. As the clay rock breaks down and the pyrite gets exposed, then weathering proceeds. As air and water reach the mineral surfaces, they weather, they form sulfuric acid, which dissolves more rock, and so we end up with acid-rich and high metals waters. As the acidic, metal-rich fluids reach the atmosphere, they combine with other fresher waters like rain or snow, and minerals will then precipitate from the solution. In this slide, you can see iron hydroxide minerals in an iron bog. What you see here are rimstone pools, like the pools in Yellowstone Park. But in this case, the rims are composed of iron hydroxide minerals. The dissolved iron in the water combines with oxygen in the atmosphere. They turn to stone, and they form a rim which pools up water behind it. That's why it's called a rimstone pool. These iron hydroxide deposits themselves are called ferrocrete. In this slide, you can see where the pale-colored rocks, the fragments, have been cemented together by iron hydroxides. This is typical ferrocrete. They typically form also in spongy wetlands. They form ferrocrete bogs. They can also build ferrocrete ledges. They can build ferrocrete draperies, like the draperies you see underground in caves. They can take a lot of forms depending on the underlying topography. They're generated when acidic, iron-rich waters combine with atmospheric oxygen and other higher pH waters like rain or snow. They can only form when the pH rises above about pH 3.8 to 4. These iron hydroxide minerals sometimes cement together other materials. They can cement together other rock, like you saw in that slide, but they also can include leaves or sticks, even small furry mammals that are too slow. Anyway, debris of any sort, anything that gets caught in that area can wind up in the ferrocrete. All of this, you might say, is nature's way of managing sludge. Ferrocrete deposits can build up to many meters in thickness. As I said a minute ago, they can take a lot of forms. They can coat cliff walls. They can build out over the topography. They can build up and plug drainages, like in this photo. The iron hydroxides can fill a drainage like this, cause the stream to meander and move off to one side. Where they're abundant, they can shape the topography. They build layer upon layer like a shifting delta. And in time, they can form a competent mass, just like concrete. Where acid drainage spills out onto the ground surface, it can acidify the soil and kill vegetation. In this scene, you can see where trees and vegetation have been killed off, and the soil's been stripped away. These areas can reach a steady state where the area of soil and vegetation die-off will grow at a somewhat constant size, but the actual area of vegetation die-off will shift as the acid drainage combines with the high pH waters, the rainwater, and precipitates a kind of a shifting platform of ferrocrete. And one feature that I haven't yet mentioned is the water quality that comes from the areas that produce natural acid drainage. Typically, this water quality varies from season to season, so that's important in your sampling. It can also vary in quality from year to year. That also will be important in your sampling. It can also vary daily or diurnally due to the variations in sunlight. This sunlight helps mediate certain reactions. I'm only going to talk about the seasonal variations, but you'll need to consider a lot of those other features. In the following slides, I'd like to show how metals concentrations and pH will change with the season and change with the flow in the waters below a mineralized area. On this diagram, the horizontal axis represents time, and I've shown a period of 1 year. On the vertical axis, I've shown relative flow. There's no actual scale on this because this really could be just about any stream. In a moment, I'm going to overlay the metals concentrations and pH. And in this case, let's say these data are from the Alamosa River, and they represent a combined flow from several streams. This is the flow for the area that I've been talking about in the previous slides. The data here are a combination of several streams. As you can see, the flow begins to rise from a base condition starting in about April. It peaks around June, and then it falls back to a base position around July. And then after that, it rises very slightly again around September before falling back to its base rate for the winter. Now that first flow peak, which is the larger peak, represents the spring flush. This is when the snow is melting. This occurs as the snow recharges, the snow melt recharges the river. The second peak, which is a smaller peak, represents late summer storms or monsoonal storms. And those monsoon storms don't always occur. Now in this slide, I've overlain metal concentration. In this case, I've shown iron, but other metals have a similar characteristic pattern. I've omitted the scale because the concentration can vary from year to year, and depending on local climatic conditions, and also on the previous year's snowfall. As you can see, the metals concentrations spike significantly just as the hydrograph begins to rise. The concentrations fall a bit during the peak flow due to the dilution from more neutral pH waters. Then they rise again on the waning limb of the hydrograph as the rate of dilution recedes. During the monsoon season, if there is a monsoon season, the concentrations will also rise and then will recede back to the base level. Now I should mention that metal concentrations also rise with each rainstorm, but I'll let those data off for clarity. Those are kind of one-day events. In this next slide, I've superimposed the pH over the previous two slides. This shows pH and flow and metals concentrations. And notice how the lowest pH on this graph occurs during the winter. That's the period of the lowest flow. As the spring flush appears, it washes in waters that have the pH of rainwater or snowmelt, which in this area is about a pH of 5.5. So the pH during that time rises. That's the pH of the spring flush, and it's up to its highest levels. And studying these graphs, you probably would realize that water quality will vary significantly depending on the time of year that you take your samples if you're downstream from acid drainage. So for sampling to be representative, you'll need to collect samples throughout the year. If you're planning a mine cleanup and need to know about the water quality, or if you're evaluating a permit application or needing to know about water quality, you'll need to consider these features and vary your sampling accordingly. You'll want to cover all of the seasons. So what about mine waste? Waters that flush from pyritic mine waste or tailings, or from the exposed workings even, can have the same kinds of features and environmental effects as the natural acid drainage. Depending on the overall grain size and exposure of the mine waste to air and water, the rates of weathering can vary between the natural areas and the waste rock. But the weathering chemistry is the same. The waters that flow out of the pyritic waste rocks may be high in metals during the first flush or after thunderstorms. Mine waste would give you that same sort of flush. So remember, knowing what metals are in the waste rock and understanding the conditions under which they mobilize can tell you a lot about when and how to sample and about the potential environmental effects of waste rock weathering. So back to you, Dave.
Thanks, Harry. That was great. And those are great pictures of Alum Creek. Interesting area.
Oh, it's a beautiful spot.
Yeah. Well, at this point, we're going to take a 15-minute break. When we come back, we're going to talk about geochemistry as well as sampling and monitoring. If you've got questions, go ahead and fax them in during the break. There's lots more coming up. We'll see everybody in a few minutes.
Okay.